Everyone, my name is David Stewart. I'm from Approve. I'm going to do this presentation with my wonderful colleague Skip. Approve is a security solution focused entirely on mobile apps and the APIs that service those mobile apps. So this is what we breathe every day, and we're going to talk about keeping secrets today. What happens when mobile apps and APIs share secrets in ways they shouldn't, and what you can do about it. So let's get into the agenda. We're just going to cover quickly a couple of different things. I'm going to give you some high-level context as to what we see generally in the mobile space, and then Skip's going to give you the details of what goes on and what you can do to improve how you secure the secrets that you need in your in apps and APIs. So first of all, we're going to talk about what makes mobile different, and in fact, let's just do that and go on to the next slide. So a couple of things to notice about mobile apps and APIs, and these might be a little bit unusual. Certainly, this one is that the APIs that service mobile apps are generally quite complex, rich in the capabilities that they have, but something that people don't always realize is the app itself almost is like a self-limiter. It prevents because when you're using the app, there's a limit to what you can do. You're typing things in on the app, therefore you can only be logged in as one person. Therefore, you can only do certain functions. But when the app is taken away and something else connects to the app that has more flexibility, more broadness, it can sometimes unlock all kinds of data within the backend systems very easily and very quickly. And so the app, when it's present, actually provides a little bit of a bottleneck, if you like, in how much data can be sucked out of the backend systems. So this is an important thing to realize. We're going to go on to talk about bots and scripts and how they interact, but I just want to make that simple point that the mobile creates this situation which is quite unusual, and people sometimes don't realize it. The second thing I want to talk about is on the next slide, which is about what happens when you deploy your apps. You, generally speaking, deploy them through the two major app stores, and it's an odd situation because you're actually providing that code and anyone can download it. They don't have to identify themselves, and they can spend as much time as they want digging around in that code. And it turns out that the app code itself becomes a real treasure trove of interesting stuff that the bad guys can play with. Now, you might be thinking, oh yeah, you're talking about secrets and storing secrets in apps. And I am talking about that, but I'm talking about a lot more than that, because in the app, and by studying the app, you can learn a lot about the APIs, in fact. So think about playing with the, operating the app in a normal way, but looking to see what kind of the relationship between pressing buttons in the app and API calls being made, and then data coming back from the back end gives you a really clear understanding of how the business logic works within the app. And that then allows you to think about how you would manipulate that business logic for your own benefits. And so you've got a situation here where you don't know who's looking at your app, you don't know what they're doing with it, you don't know how much time they're spending on it, and they might not be simply reverse engineering it to look for stuff that's inside the code. They might just be playing with it in order to understand how your API works. So it really is an unusual situation where you kind of give your code to somebody and you don't know who they are, and you don't know what they're doing, and that creates some challenges on the security side too, as I'm sure you can imagine. So next slide. Yeah, this talks about the kind of the range of attacks that we see in our everyday life, dealing with all the customers that we have across many different sectors. Obviously, because of the type of work we do, the customers that we have rely heavily on the mobile app for interfacing with their end users and customers. So it's a very important channel for them. So simply put, the three different types of attacks you can see is modified mobile apps. So somebody's taken the app, reverse engineered it, repackaged it to do something slightly different, and then perhaps managed to get it into the App Store and maybe get people to download it onto their apps. So then they have an app that looks like the genuine app, but is actually doing something different under the hood. Second thing we see is people taking the genuine app but manipulating it. In other words, running it on a compromised mobile device that they control, and making it do, intercepting the data, changing the data, making it do things that it wasn't designed to do. So it is the genuine app, but it's being manipulated to feed it with data and extract data in ways that wouldn't happen in a normal situation. And the third one, which is actually the most common that we see, is scripts and bots impersonating mobile app traffic. So all that research that I talked about that the bad guys do when they download your apps and play with them and interact with the APIs and see how all that works is all a precursor to building a script which will then be used to attach to the APIs, completely bypassing the app. So the app won't be there at all. And then they will be able to quickly and flexibly change the things that they're doing as they probe the back end via the API to try to extract, to do whatever it is they're trying to do. It might be to take over accounts, it might be to extract data, it might be to bring services down, etc. So they can use the data, all the information that they've collected to build a script, and it's the easiest attack to make. We're not going to say that the criminals are lazy. We're going to say that they're efficient, which means that they will go after the easiest target. So they'll go after that easier bot scripted attack. They could go for the modifying mobile apps, but that's a lot more work, and there would need to be a really good reason for them to go there. So that's the kind of stuff that we see. Moving on to the next slide. So just again, finishing the context of what I'm talking about is that generally speaking, the perceived idea of securing the mobile end-to-end channel is to do user authentication, to have an API key, which is how the app identifies itself to the back end, then have an encrypted TLS channel into the API endpoint. And what we're going to see, and what Skip's going to go into in a lot more detail, is to make it clear that that is not sufficient. And if that wasn't evidence enough, and if you don't believe me, then the next slide is some independent research on the topic. This is a report that was done by Osterman. It's actually available on our website if you're interested in it. It is independent research, although we sponsored it. And it talks about some of the many. This is just one example of the sorts of data that's in there in terms of use of API keys in mobile apps, for example. And we're actually doing some other research now, which we hope will be out in a couple of weeks, which may shed some more light on this in terms of how many people actually do have API keys in the apps. And we suspect the percentage is a little bit higher than people have declared here. So either they don't know, or they're being economical with the truth of the real situation around API keys. Anyway, that's enough for me for now. I'm going to pass over to Skip and let him dive into a bit more detail on this.
Thank you, David. So what I'm going to try and walk you through is what I think is best practice to minimize the exposure of API keys and secrets, and also as a side benefit, you a lot more ease of actually managing those secrets during operation and changing them rapidly across your entire user installed base. So typically people look at putting a lot into their back end, into their API server, but what they often are missing is that there's a large attack surface that emanates across the channel from that API service into the app itself, which is running on a device. So these secrets are live. They could be statically embedded in your apps. They could be saved to persistent storage in the app. They could be exposed on API calls running across open or inadequately secured channels. And unfortunately, they're often accidentally left in repos, which people are quite often harvesting to grab all sorts of interesting keys and credentials. So what we're really after here is to try and lock down these additional attack surfaces. Is the device running safely, it hasn't been compromised in any way? Is the app the actual authentic app that's running? And have we really locked down the channel effectively? So I'm going to build up here. First, if these secrets are present on an app and they're easy to observe and steal, the first thing I'm going to say is never trust an app to keep a secret. So if you can, how would you not actually have secrets on the device, or at least have them there as short a time as possible? And I'm going to use a classic sort of computer science indirection move, and I'm simply going to take all the secrets off the app and I'm going to put them up in a service. And in this case, the shapes are sitting there. And whenever, in this case, the shapes app would like to make an API call, in this example, to a backend shape service, rather than grabbing that secret statically on the app, it would actually call up to this secret service and say, give me the latest API key. The API key would come down. That would be rewritten into the API call. And then the API call would proceed entirely as normal. So there's a great advantage to this in that you have secrets out of the app itself. It's no longer statically in code. It will no longer be stored at rest anywhere on the device. And a very important advantage is that now these secrets are up on a secret service that can be accessed by your ops procedures. So you can freely change this API key as often as you want. And every time your app calls for the API key to add into its runtime for an API call, it will get the latest key. So you might not want to ask for a key with every API call, but what you would like to do is maybe update every few minutes and ask for a fresh API key to be served. So if there's any change, you would get that across your entire installed base within just a few minutes. So this is great, except how do we make sure that the only thing that can get access to the secret service is a genuine app? If a bot or a hacker had access, we've now made it really easy for them to get as many secrets as they want. So we've started to solve the problem, but the second leg here that we have to operate on is how do we authorize just that app to make the call? And in fact, the app and the environment it's running in are sort of the key. Rather than imagining having a static API key, we're going to actually use what we have running to authorize itself. So there's a concept of attestation, and we're actually going to use attestation services to prove that the apps are authentic. They're the original apps downloaded from the app stores, that they have not been manipulated in any way or tampered with. And also that the environment that this app is running in is secure, that the sandbox models in Android and iOS haven't been compromised in any way. So you've probably, if you're a developer, seen a number of independent packages where you can actually check the signature of the package that is downloaded into to install the app. Or you may have seen some root and jailbreaking detectors that are trying to check some of the runtime environment properties. And these are examples of pieces of what you would want to do in building up an attestation service. Unfortunately, these tend to require frequent maintenance to keep up, and so they are interesting packages, but they really don't stand the test of time because hackers are not standing still. Both Android and iOS have native attestation type services. They've been evolving over time. They started kind of making sure that the device itself was integral, and then they have added some checks to make sure that the apps themselves are also as expected as downloaded from the stores. They don't cover everything. They're not moving as quickly as the hackers are moving. And also they're not available in all markets. For example, on Android, if your market does not support Google Play services, then you won't have access to Android Safety Net or Play Integrity. Also, you have to be running on a modern enough operating system to pick up either the Android or the iOS services. So they're valuable, they're a great base, but really for the best sort of state-of-the-art attestation services you can get, you want to go to a commercial solution. Here, these companies are making money by keeping pace with the hackers as they're moving forward. They'll offer the app and device attestation services. In addition, they will add some security into the channel between the apps and the backends. They will typically optionally integrate safety net and device check if your industry requires those checks to be run. And importantly, they'll ease the developer's experience. The APIs for these kind of attestation services can be quite complex, and this provides usually a uniform wrapper around these. So if you do this, you can prove that the app is safe and has not been tampered with, and it's running in a safe environment. So you're going to combine that attestation service with the secret service. So now the app and the environment will actually be the key that authorizes the release of those secrets. So when a Shapes example in this case wants to make an API call, it would actually call up to the attestation service. The attestation service would challenge it to provide some answers to some questions, which would cryptographically prove that the attestation is acceptable. At that point, the authorization occurs and the secret can be downloaded and passed through. This works great with your API services. It also works well with third-party services that are using these kind of static API keys. The good thing is that the API key itself is not ever at rest in the app or in storage somewhere. So I'd like to make one improvement here. The API secret is still present in the runtime. If you have control of your backend, then what I would suggest doing is, rather than exposing the key in the runtime itself, you can do a little bit better by actually using that secret to sign a short-lived JWT token. At that point, the token would be passed rather than the API key, and that token would then be checked in the back end in the same way that the API key would, except in this case, you're just validating that the token is still live and also that it has been properly signed by the secret. So the secret is known to the attestation service and to your backend, but the secret is never present anywhere near the device or in the channel itself. The third step, we've sort of proved the safety of the app and the device, but what we haven't done is considered the communications that are occurring between the app and the endpoint. And a very popular attack is a man-in-the-middle attack. So if an attacker can not, for some reason, find secrets in the app itself or reverse engineer or tamper with the app, then man-in-the-middle is becoming more and more the easiest way to go to extract secrets. So you will most assuredly probably be doing a TLS or HTTPS connection, which will encrypt the channels. But with mobile devices, what a man-in-the-middle attacker will do, since they bring their own device here, they're just trying to find a secret in the app, they will actually pollute the device's trust store and add their own certificates into that trust store. So when the TLS handshake is taking place and the app is looking for the certificate that proves that the service is what it claims to be, the man in the middle will say, oh, I'm your Shapes service, and will present a certificate to the Shapes device, which will then go look in the corrupted trust store and will say, oh, here is a certificate which does validate that this is the expected service. At this point, the man-in-the-middle attacker can easily decrypt the TLS coming off, take a look at things, manipulate them, doing whatever they want to it, and just observe. It's a great way to hack credentials and also to reverse engineer APIs. So how do you block this? The typical best practice way is to add certificate pinning to your app. So at this point, you will assume that the trust store may be corrupted, and you will add a specific certificate or a hash of the public key of that certificate into your app and your network stack, and you will actually pin the service so that this time when the TLS handshake takes place, in addition to looking in the trust store, you will also check and see, is this the actual certificate that I'm expected that's being presented? And this is another sort of static secret. It's not so much a secret as it is static. So you want to do the same principles using this sort of indirection service here. So we'll actually download the Shapes certificate, the Shapes service certificate here, just like another secret. And that ensures that it's only in the runtime. And the most important advantage here is that it now makes this perfectly dynamic, so that if you want to rotate certificates or to replace certificates if they expire, you can easily do this across your entire install base through this service. So it makes everything dynamic. And one of the big challenges with certificate pinning is the risk that you will lose access to your app. The app will essentially brick if these pins expire. In this case, since you have access to these pins through the service, that will never occur, and you can rotate them as needed. So how easy was it to steal secrets? Pretty easy, but best practices, I think, go a long way towards reducing the exposure. And because you're now able to manage your secrets very easily using sort of runtime operations, I think this is a very effective security operations technique for mobile secrets. So we started saying never trust an app to keep a secret. And we actually took those secrets, moved them off the device, and only served up-to-date secrets or their short-term, short-lived tokens into the app only when needed. We needed a way to authorize to make sure only a healthy app is the only thing that can access those secrets. So we used attestation techniques to regularly and frequently attest the app and device integrity and to authorize those secrets. Lastly, we needed to ensure that nobody could cut in and man in the middle these secrets as they were going between app and the backend service. So we introduced certificate pinning with the added benefit that we can now dynamically change those certificates as needed. So we no longer have to fear bricking your apps. So I think we've demonstrated what we believe is best practice for keeping your secrets out of a hacker's hands, allowing you to manage your secrets just as any other operations technique that you would use. You can change all these things on the fly, and there will be no impact on customer experience. So with that, I'd like to hand it back to David.
Thanks, Skip. That was great. So this is actually the final slide. So really what I'd like to suggest, first of all, if you're one of these, if you're a developer who is fed up being told not to put API keys and other secrets in apps, but doesn't know what else to do with them, then we have sympathy for you, because we understand that the issue is not storing the keys in the app. The issue is looking after them, both in the app and also when they're in motion on the API, and making sure that you've thought about how you're going to defend against the app, those secrets getting into the hands of bad people. That is the key thing to think about, not how you're going to hide it in the app, but rather how you're going to make sure if and when it gets out that it can't be used. So we'd like to encourage you, if you're on the DevOps side, not to blame developers for doing this, but rather let's look at some of the techniques that Skip's described as ways in which the secrets can be protected, so they can't be abused at scale, which is really the name of the game here. So please check out our website, approve.io, where you'll see all the features that Skip's talked about. The resources page is a great place to start, where you'll find white papers and videos and all kinds of interesting stuff there. If you want to get a meeting with one of our security experts where you can discuss your own use case, then there's a form on the website again for doing that. And indeed, there's a free trial if you want to try Approve out as well. It's a standard SaaS product. You don't need a credit card to sign up for the trial. So we do have some questions that I've already answered, but we did get one about, why can't the hackers break the attestation? So I'm going to pass that one to you, Skip, for the last thing. So if you can give us some thoughts on why the attestation isn't easy to break.
Okay, a couple things. First of all, typically when you're trying to protect a mobile app, you can try and protect it from being tampered, and you can detect whether it's been tampered or not. And it's much easier to detect it than it is to prevent it. What we do with our approach to attestation is that we don't try and protect the entire app, but we harden very effectively the SDK that we use to interface between the the application and the services that we're using. So we're very strongly focused on hardening that. The first thing that happens is that the SDK will check and make sure that it has not been tampered with. And secondly, it will then go out and check the source code and then eventually the environment. Secondly, the actual security decision is made off device. And this is very important so that you can't use instrumentation frameworks and other techniques to try and hook a function call and say, that's okay, this is really fine, please proceed. Instead, the decisions are made off device and tokens are returned to the device. So it's very difficult to reach out into the service and tamper it. Third, there's a very strong challenge and response protocol where there is a sort of cryptographically randomized approach that requests a random set of measurements that completely cover the integrity of the device. They change each time. So we've worked very hard to do that, mask all the protocols, do everything, all state-of-the-art stuff. So it's probably possible to reverse this technique, but it would take centuries. And we've been running for multiple years now with this, and no one's come close to doing anything like that.
Yeah, I think the key thing is attestation is a thing, but it's how you implement it. And of course, there are different implementations. So what I'd suggest, the person that asked that question, if you want more information, please get in touch and we'll be happy to talk to you about this. We have patented technology in this area. So we think we've got a lot to offer. So please talk to us if you want more proof that we got something good here. Okay, time's up from us. Thank you very much for attending, and you know how to find us if you want to know more. Thanks, Skip. Thanks everyone.
Everybody.